In just about 1 minute, we're going to start another technology showcase session. You're going to be, again, getting into some of the important details that are involved, which is why many of you are here. I'm kind of the big picture person, if you will. I'm dealing with the larger picture of what's going on here, but I'm learning so much, which is great for me, being a non-expert coming into this topic. When I leave here, I think my brain will be exploding. It's really quite fascinating. Anyway, yeah. So we had some technology showcases yesterday. One of the presenters of a technology showcase is actually going to be doing this next half hour of presentations, so I'm not going to have to go into the details of what these presentations are. That's going to be led by Fridtjof Hennemann of True Ocean, whom you saw yesterday, and I give the floor to you.
Thank you, Terry. Yeah, thanks for introducing me again, Terry. Good morning to the audience. My name is Fridtjof Hennemann from True Ocean, and I have this morning the pleasure to represent you technical showcases this morning. We will take this next half an hour to have two speakers for us presenting their interesting showcases, and I don't want to steal too much time from them, that we have sufficient time for their 10-minute presentation and sufficient 5 minutes for questions and answers. So our first presenter is Peter Nieuwveld from Fugro. Peter is a solution owner of UXO innovation at Fugro, and with a background of geomatics. And Peter is part of the UXO risk mitigation team and co-coordinates the research of Fugro's projects in the fields of UXO detection, identification, and clearance. And please, Peter, I ask you to the platform.
Great. Am I on? Can you hear me? Yes? Thank you very much for the introduction. And good morning, and thank you very much for the opportunity to address you all, and to those who've joined us online as well. As mentioned, my name is Peter Nieuwveld. I'm the solution owner for UXO innovation at Fugro, and what that basically means is that I get paid to become very excited about all sorts of new technologies and innovative ideas that will help us to detect, map, identify, and ultimately clear marine munitions. Now, Fugro is a geodata company, and what that means is that we realize that in order to build and operate any asset anywhere on the planet, you need to at least be able to acquire and understand geodata to some level. And we are the world's largest geodata company. And with the onset of the energy transition, we've started to work over the past decade or so for an increasing number of clients in the offshore wind energy industry. And that's the first time that we come across, really, this problem, this challenge of UXOs in the marine environment. And that's where Fugro started to get involved in the industry. We suddenly had a significant group of clients who had a problem, a risk that they needed to manage. And being a geodata company, we were well placed with expertise and equipment to be able to help them with that. And so what came out of it eventually was a comprehensive UXO risk mitigation solution that we've put together, and it basically offers services to these clients across the board, from the beginning of the process with desktop studies and geoconsultancy to plan a project, all the way through the steps of mapping and survey to acquire data on potential UXO targets, identifying those UXOs, and ultimately, in the jurisdictions where we're permitted to do so, clearing them from the oceans as well. And we will sign off on an ALOP certificate where it's required. But that's our context. Our context is ALOP certificate delivery, essentially, in the wind industry. Now, if you think about a wind farm, for instance, the Borssele wind farm off the Dutch coast, the entire wind farm area is approximately 344 square kilometers large. And in order to survey and clear that area to ALOP level is well over a year's worth of survey work and clearance work for a single vessel. By comparison, the Baltic Ocean is more than 1,000 times larger than that site. And if, as a community here, our ambition is really to rid the world's oceans of munitions, we're going to have to survey and clear a significant area of seabed. And in order to do that, we have to start thinking very differently about innovation. To do it in old traditional ways using current methods is going to take a massive number of people, significant numbers of vessels, specialist equipment, and what we'll probably end up doing is damaging the ecosystems and environment that we're ultimately trying to protect. So we have to think about innovative ideas to tackle the problem. And any kind of new solution or part of the solution that is going to be viable and stand any chance of making a real meaningful impact needs to be efficient, especially in the amount and speed at which we collect data and our use of resources. It needs to be sustainable, but with particular reference to environmental sustainability. It needs to be safe. We need to reduce HSE risk and exposure. Using that many people in the offshore environment is obviously a significant risk which needs to be mitigated, but also systems need to be safe for navigation, and they need to be safe for other marine users that will from time to time come across these solutions. And ultimately, it needs to be scalable. One ship is not going to make enough impact. We need to be able to quickly and easily replicate these solutions and manage them at large scale, including the data that comes from those systems. Now, at Fugro, we believe that there's a future for remote and autonomous working. And what comes out of our investment in this area of technology that's relevant to this discussion is three primary building blocks, really. Uncrewed surface vessels, which can be equipped to carry out various tasks. But we also need to be able to operate and safely manage those vessels, for which we have a network of remote operations centers. And ultimately, like I've mentioned before, we have a massive amount of data that will come from those, and efficiently managing and processing that data is the third aspect of it. Now, we've been investing in remote robots and sensors for a while now, and the three that you can see on screen is really what comes out for the future of marine munitions clearance. The first element really is what we've called the Blue Essence uncrewed surface vessel, the USV. Now, the Blue Essence is a 12-meter-long vessel which can be equipped with a multitude of different survey sensors to carry out various different tasks. She's got an operational endurance of about 3 weeks at full operation mode, but about 150 days at transit speed, and significantly more environmentally friendly than an equivalent traditional survey vessel. She can be equipped with a number of sensors, but she can also deploy other systems. So she can deploy, for instance, Fugro's new Blue Volta electric ROV, which you see at the top of the screen there, which is a custom designed and built system. It's approximately the size of a traditional observation class ROV, but it's designed to manage the full data throughput of a much bigger working class ROV. And so it's flexible enough to deploy a number of different survey systems and to manage the data streams and data volumes that come from those systems. And Fugro has been working with AUVs, autonomous underwater vehicles, for a number of years already, and those can also be deployed from the Blue Essence. In order to manage them, Fugro has developed 8 different remote operation centers around the world, and those are currently operational. And over the years, we've amassed more than 250,000 remote operational hours. So we're building up experience as we go along and understanding and learning more about how these systems need to work. They're distributed across the globe, and so you can see that we have global reach and global capability, but also it gives us geographic redundancy so that events happening in certain parts of the world do not have to compromise the safety of remote operations. We can operate from anywhere in the world. And finally, the data element. Fugro uses our ship-to-shore data transmission technology to transfer data directly from vessels acquiring data offshore up into the cloud and ultimately down to the shore-based processing teams that need to work on that data. And at that point, we start to use machine learning as much as possible to enhance the capabilities of our processing teams and to aid them where possible. So far, we've developed and released 2 machine learning algorithms to help us do that, and we're actively working on a number of other task-specific algorithms as well. And we see a big future for machine learning and AI-driven assistance. Now, this is not new for Fugro. We've actually been developing the technology required to run these solutions for more than a decade. And Fugro has been actively marketing and offering remote services to the industry for more than 6 years, starting initially with office-assisted remote services, OARS, and the relatively simple cases of offshore positioning. Now we go onto a vessel, we install some positioning and telemetry equipment, and then off goes the vessel, and we monitor its position and send positioning instructions and quality information back to the vessel from a shore-based location, and that's where we start. And over the years, we've been offering more and more remote services and continually pushing the boundaries of what's possible through remote operations, and to the point now that we carry out full subsea asset inspections with ROV pilots sitting in an office on shore operating assets offshore, and the entire inspection team sitting in the safety of an office. Last year, we released our remote expert and remote client services, where a client representative can essentially sit in the comfort and safety of an onshore office and have a full view of what's going on an offshore vessel and continuously monitor the data that's coming into that from that vessel, assisted by the Fugro team in the office with them, and it's significantly safer. And we also last year started for the first time operating USVs. This year we've started operating now Blue Essence, our slightly larger USV, and in conjunction with that, the Blue Volta ROV. And that's not where it ends. For us, our ambitions are much bigger than that. This is kind of the starting point. And we definitely have ambitions to extend this technology and this remote and uncrewed working method into the realm of marine munitions, identification, mapping, survey, and ultimately clearance. It might sound like a nice, fancy, futuristic idea, but it's not, because we're already doing it. Like I just said, we started this year operating the Blue Essence USV for the first time, and in April this year, Fugro conducted their first fully remote and completely uncrewed remote pipeline inspection off the coast of northwest Australia. The Blue Essence was deployed to undertake survey tasks along the pipeline route, and she also deployed the Blue Volta ROV to carry out visual and cathodic protection surveys along the pipeline route. And it was completely remote controlled. Not a single person went offshore on the vessel. And the operational team that carried out the work and controlled and managed the vessels and the equipment on board were located in our Perth Remote Operations Center, 1,500 kilometers away from the survey site. Over the course of a month, the vessel sailed 1,300 nautical miles in and around one of Australia's busiest resource ports, and she only burned 3,300 liters of fuel. That's 97% less than the equivalent traditional survey vessel that we would alternatively have used for this work. And the whole project completed with 0 incidents. So, in general, we see it as a huge success for this technology. So, from our perspective, remote and uncrewed operations really have a bright future, especially in the area of munitions clearance, where we need significant resources and we need to become more efficient in many ways. The technology is efficient, especially in its use of resources. It's sustainable, especially considering the massive reduced environmental footprint of the operations. It's safe, a massive reduction in HSSE hours, but intrinsically by design it's safe for operation offshore in busy ports and shipping lanes. And not only is it scalable, but it's already being scaled. Our second Blue Essence USV is currently mobilizing in Aberdeen and will be operational by the end of this month, and we have 3 more units in production. By the end of 2022, we'll be operating 5 of them globally, and we're in the process of designing a larger, more capable vessel to carry out other, more demanding tasks. Not only that, it's built on real technology that exists, as you've just seen. It's built on a massive amount of experience, and it's recently been proven to be a viable way of working on commercial projects. So, with that, I conclude my talk, and if we have some time left over, I'm happy to take some questions. Thank you.
Yes, Peter, thank you very much for these very interesting insights into your technology, and I'm always amazed to see this. And this is also something we speak a lot with our business partners, and we try to convince them this is not science fiction any longer.
Yeah, absolutely.
It's actually there.
Yes.
So when we look at this very fascinating, impressive technology, many will maybe question on the maintainability and how can it be operated and where's the limits of operation. As we know already, crew transfer in wind offshore, you have a significant wave height and then all this operations is gone. Can you already from your experience in first trials report a little bit on these limitations. Is this similar to what we know today in the operations, or even better?
Yeah, well, obviously the biggest difference is that there's no crew on the vessel.
Yeah.
So the first thing you'll notice is it's fully compliant with marine requirements for safety and navigation, etc. But it doesn't have that whole aspect of SOLAS, safety of life at sea, because it doesn't have a crew. And so you already don't have any aspects of crew transfer and things like that. Now, it's designed for use in coastal waters, so it typically has a home port that it will need to return to, just like any vessel will need to return for refueling, for resupply, etc. But it will need to, during the course of its operations, return to port, where a maintenance crew will be on standby to check systems, make sure that it's safe. Obviously refueling needs to be done safely and manually, and things like that. So on shore, there will be a contingency of support personnel to assist in the running and maintenance of this vessel. But when it leaves port and carries on, it's fully controlled by human operators. There's always a master mariner in charge of the vessel and in control of the vessel, but they just don't sit on the vessel. So, yeah.
Yeah, impressive. Yeah, I also liked in the terms of sustainability, the numbers you have shown, the reduction of opportunity fuel would have burned with other survey vessels. So maybe even is there thoughts of replacing even the combustion propulsion to some electricity in the future?
It's already a hybrid propulsion system that runs this thing. So it's actually a battery electrical drive vessel, but it is continuously using marine fuel to run combustion engines to regenerate that electricity and keep the batteries charged. So the propulsion is hybrid at the moment. Fugro is ambitious in reducing carbon footprint and emissions. So we are looking at alternative fuels like biofuels and things like that. And ultimately, if alternative fuels become available, we would be very interested in replacing that element of the system. But we're being as forward-thinking as possible at the moment in terms of alternative propulsion systems and fuels as we can, whilst practically still being able to achieve our ultimate goal of executing this work remotely.
Okay. I just looking into the audience, is there any questions from our online guests? Not at the moment. Then Peter, thank you very much for this really big insight in this huge technology which will help running assets offshore in this demanding environment. And I'm sure there will be more context afterwards in the break. Thank you, Peter.
Yes, thank you very much.
So now I have the pleasure to introduce our second presenter, Peter Rabenecker. Peter Rabenecker is the deputy head of the Department Applied Electrochemistry from the Fraunhofer ICT. I haven't seen Peter yet. Is he here? Ah, he's remote. I didn't know.
He's online.
Thanks. Peter, welcome here. Good to see you here. You are joining us from remote. Thank you very much. Peter, just to introduce you and to finish it off, you're a chemical process engineer, and you're already working for 20 years in detection of explosives with the focus of electrochemical sensors and trace detection, and the stage is yours. Thank you very much.
Thanks for the kind introduction. I will start to share my screen. Okay, I hope it's visible now. Ladies and gentlemen, I'm the second Peter here in a row to show you a technology showcase. And first of all, I want to use a few seconds of my short time to thank the technical team, because a hybrid conference is very tricky, and I think they're really doing a good job here. So thanks. What I want to show you today is our work regarding an electrochemical sensor system for the detection of explosives in seawater. We already heard the word of chemical sensors yesterday, also today, and I want to give you a few more details about this technology, hopefully without any exploding brains afterwards. So, okay. The picture on the right shows a human tongue. just to imaginize that how our sensor works. Our sensor tastes or it smells the target like dogs would do when they are looking for explosives on land. So, but please keep in mind, this sensor is no commercial product. There's still some work to do with that sensor, but today I just wanted to understand what our technology can afford and where the limits are. So the agenda will be just a few words who we are and where we come from, how this electrochemical detection works. I want to show you some of our experiments that we have done, and also one slide for the future challenges and ideas we are planning or having. Okay, so I guess everybody knows Fraunhofer, since it's Europe's largest application-oriented research organization with, in the meantime, almost 30,000 employees. The Fraunhofer ICT, Institute Chemical Technology, is located in Finstal, close to Karlsruhe. And as you can see in the upper left corner, quite on the other side of Germany, related to Kiel, so I'm quite far away. The ICT is working with explosives for more than 50 years now. And as you heard in the introduction, myself for more than 20 years by now, time's flying. So, and since we have this long history of research with explosives, I think it might be interesting for you to know that we, besides the project I will show you later, we have a large data set for all around explosives regarding solubility, temperature influence, pH, salinity, or distance from source, what you can expect, what concentrations you will have there. Also vapor pressure and humidity, but that is not relevant in the maritime environment. So now we're here at electrochemistry. So what is electrochemistry? All of you know the everyday life. If you have some iron and some water present, then you have some electrons moving, some oxidations, reductions, and what you get is rust. So that's the basic electrochemical process with electrons moving, just to get you to the picture here. Okay, most of you will remember the school experiments with electrolysis. You have 2 electrodes dipped in an electrolyte. Then you put some cables on it and the voltage source, and then you increase the power step by step. So, and at a certain point, you can see some bubbles evolving on the electrodes. So the message here is the power that is applied, the voltage that is applied is an energy, and different things happen at the electrodes at different energies. Okay. And that's the thing we are using with our sensor system. So our measurement parameter is, in fact, the electrons that are moving that are moved during an electrochemical reaction. So we are measuring directly what happens with the explosive on the surface of our sensor system. The key message here is you can't use it for standoff detection, or you can't also use it for a large area screening, but you can do quite good punctual, very sensitive measurements. But we need the molecule to get to the sensor surface. That's important for the technology to work. Okay, probably you might say, okay, forget it. But to show you that electrochemical detection is no rocket science and no expensive technology, some commercial electrochemical-based sensors are blood sugar sensors for glucose monitoring, and also some personal safety equipment sensors, or also alcohol testers for drivers. So you see, when you're looking at the blood sugar sensor, it's a small, sensitive thing. It's quite cheap, mass market driven, and it only needs a small drop of sample for the analysis. Okay, so here are a few numbers for electrochemical sensor, what it can achieve. So as I said, only a low amount of target substance is needed for the analysis. No need to sample some cubic meters of air or water or something like that. What we need for the detection in the case of TNT is we can measure 40 parts per billion in the sample. Our sample size is 1 milliliter in the seawater. We can live even with less. And so the absolute amount of substance that is needed is 1 nanogram. That's 10 high minus 9 gram of explosive target substance. So let's move to also here pictures from the real life. No nice drawn pictures. What we have done so far, we have set up sensor systems. As I said, they are focusing on the explosive itself. And what we wanted to do is we wanted to detect fresh mines or improvised explosive devices or unexploded ordnances, something like that. We developed 2 different systems, one suited for an AUV and one for a remotely operated vehicle. Mr. Kalthofen showed you yesterday, from Atlas showed you yesterday the CCAT. That is also pictures of the CCAT where our system was integrated during sea trials. And the remotely operated system is using power supply, data supply from the vehicle. And the autonomous system has everything on board. You can drop it in the sea and get it again a few hours later. And it does all the things by itself. And also it's a self-learning system that is getting better and better the more you use it in the relevant environment. We have also done many sea trials in the North Sea and also the Baltic Sea, most of them together with the WTD-71, the Bundeswehr. We were in Meldorf, Eckernförde, and Gdynia, Poland, to do some tests, also in Kolberger Heide. We were there a few times. So what we did there, a typical measurement is done like that. If you are using the CCAT here in this example, we are doing some reference measurements of the target, because seawater is not always the same seawater. In North Sea, Baltic Sea, or in the Caribbean, I haven't had the luck so far to measure there. And if the reference measurement is done, we are moving against the water current. You heard it before today. So we get the explosive target molecules transported towards the sensor. And we have measured with the old mines, but also brought out our own explosive targets. You can see on the right at the bottom. Okay, so takes me to my last slide already. A short overview. What I think future challenges for this system is the long time stability. Up to now, we have measured for 1 working day. Okay, the crew of the ship was thankful, but the project ideas are to leave it for weeks and months out there. And we have some ideas already we are working on to make that possible. And my idea how it should be or has to be, we already heard from Dr. Beck yesterday, to monitor in time and space, and also from Commander Lammes, multiple sensors systems. I think what we should do is apply a stationary or moving sensor network. And because the electrochemical sensor is small, low in energy consumption and quite cheap, we are talking about a few €100 per sensor. I imagine a big network of sensors that are measuring or are being dragged by a ship, for example. Okay, so with that, thanks for listening, and I'm here for questions. Thanks.
Yeah, Peter, thank you very much for this interesting introduction into the electrochemical sensing. I'm just looking if there is a question. Yes, there. Someone approaching the microphone. Two persons, actually. Yes, please.
Yeah, great. Thanks. Aaron Beck from Gamar. That was very interesting technology. I have two sort of quick questions. The first is, how do you deal with like naturally occurring organic matter or natural nitrate in seawater? And the second question is, since you're actually consuming your analyte, how do you deal with concentration polarization during the analysis?
Okay, so first question, the selectivity is not perfect of electrochemical sensors, but we are using many different pattern information out of the pattern of the measurement to discriminate against different organics. So, and the nitro-aromatic compounds are quite good to detect, but we have the problem of biofouling or something like that, so the contamination of the surface. So that's part of the long time measurement project we are doing at the moment. And the electrolyte is not really consumed. We are using an open system, so we are directly measuring in the seawater in a small chamber, and we can clean it by purging it, and also electrochemically clean the chamber. So the next measurement can be done a few seconds afterwards.
A few seconds is a very good line here to me. I have to interrupt. I'm very sorry, Professor Maser, but I think you can get in touch. Our tight schedule forces me to close this session of technology showcases. Thank you very much for being with us here. And I hand over to Terry for the next session. Thank you.